Hey everyone, welcome to this explainer. Today we are going on a seriously incredible journey. We're going to start way up in the macro, everyday world of raw mechanical power, and then we're diving all the way down to the microscopic, atomic level of material science. It's all about how these invisible atomic movements make our entire modern world possible.
When you think of a high-performance sports car, you immediately think of power, right? Speed, extreme forces. Whether it's just roaring down a highway or aggressively accelerating right off the starting line, the mechanical stress being generated inside that car is, well, it's absolutely mind-boggling.
And you know, all of that power really starts at the gear shift. This is exactly where human intention meets physical mechanical reality. With just a simple flick of the wrist, a driver commands the engine to translate raw RPMs into immense, just brutal torque. But you gotta wonder, what is actually taking the brunt of that terrifying force?
Well, that brings us deep into the complex transmission, which is packed with all these interlocking metal parts. Now, here's the question for you. How can those metal transmission gears possibly survive highway speeds, taking hit after hit of massive torque without just instantly shattering into a million pieces? I mean, metal is strong for sure, but under these brutal conditions, standard steel just wouldn't hold up.
The secret to their survival is a process called case hardening. If you've ever seen a section steel gear, you might notice this dark outer rim right along the teeth. By literally baking excess carbon into the very surface layer of the steel at extreme temperatures, engineers create this super hard outer case. This drastically raises the surface hardness, wildly improves wear resistance, and essentially stops the gear from failing by fatigue while you're driving down the road. But how does that carbon actually get inside solid steel? Like, how does that work?
To answer that, we have a clear roadmap for today. 1. The secret strength of gears. 2. What exactly is diffusion? 3. How atoms actually move. 4. Fick's first law, steady state. 5. Fick's second law, non-steady state. And finally, 6. Engineering the real world.
All right, so let's jump right into Section 2. What exactly is diffusion?
Simply put, diffusion is the phenomenon of material transport by atomic motion. From an atomic perspective, atoms inside solid materials aren't just sitting still. No way. They're actually in constant motion, rapidly changing positions, making these stepwise migrations from one lattice site to another. To move, an atom really just needs an empty adjacent site and enough vibrational energy to break its bonds and push right through the lattice.
Now, there are a couple of ways this happens. When we join two different metals together, say a bar of copper and a bar of nickel, and heat them up, the atoms migrate into each other. This is called interdiffusion, or impurity diffusion, and it causes actual macroscopic changes in concentration over time. On the other hand, pure metals do this too. Their atoms are constantly exchanging positions in a process called self-diffusion, though obviously you're not going to see a visible compositional change when pure metals are just swapping identical atoms.
But if a solid piece of metal is packed tight, how do atoms actually get past each other? Let's zoom in for Section 3, how atoms actually move.
There are two main methods here, vacancy diffusion and interstitial diffusion. Vacancy diffusion happens when an atom moves into an adjacent empty site, a vacancy. Think of it kind of like a sliding tile puzzle. An atom can only slide over if there's a missing tile right next to it. Interstitial diffusion, though, is entirely different. This is when an atom migrates through the tiny empty spaces, the interstices, between the much larger host atoms. Imagine a really crowded room full of people. Interstitial diffusion is basically like a tiny mouse darting right through everyone's legs.
And the absolute crucial takeaway here is why interstitial diffusion is so much faster. The host atoms of a metal rarely diffuses this way because, well, they're just too big. But small impurity atoms, things like carbon, hydrogen, or nitrogen, are perfectly sized to zip right through the metal. They easily fit into those empty interstitial positions. Plus, mathematically speaking, there are far more of these tiny empty spaces in a lattice than there are full vacant atom spots. Because of all that, small atoms move remarkably fast.
So, we've seen the atomic motion. Now let's look at how engineers measure it. Section 4. Fick's first law, steady state.
Since diffusion is a time-dependent process, we really need to know the rate of mass transfer. Engineers express this as diffusion flux, represented by the letter J. It's basically defined as the mass, or the number of atoms, diffusing through a perpendicular unit area of solid per unit of time. Essentially, it's just asking how much stuff is moving through a given window every single second.
And that brings us to a pretty heroic piece of math. Fick's first law. J equals negative d times dc over dx. D is our diffusion coefficient, which just means how easily things move through a specific material. And dc over dx is the concentration gradient. But pay attention to that negative sign. That negative sign is absolutely crucial because it tells us that diffusion always flows down the concentration gradient, naturally moving from an area of high concentration straight to an area of low concentration.
Let's anchor this math to the real world for a second. Fick's first law perfectly describes steady-state diffusion, where the flow of atoms doesn't change over time. For example, engineers use this exact principle to purify hydrogen gas. They'll take a thin sheet of solid palladium metal and expose one side to impure, high-pressure gas. The hydrogen atoms selectively diffuse right through the solid metal plate to the low-pressure side at a perfectly steady rate, while leaving all the other gases behind. It's kind of like magic, but nope, it's just pure material science.
But steady state is the easy version. Let's move to section 5, Fick's second law, non-steady state.
Ask yourself this. What happens when the concentration is constantly changing over time? Like when you throw a solid steel gear into a hot oven filled with carbon-rich gas to case harden it, the carbon doesn't just flow completely through the gear and out the other side, right? The carbon enters the surface and stops inside, meaning the concentration is shifting every single second.
In this scenario, if you chart it out, the concentration curves change drastically from one time period to the next. This is called non-steady state diffusion, and it's governed by Fick's second law. The concentration of our diffusing species, in this case our carbon atoms, is actually accumulating inside the metal as time goes on. So both the diffusion flux and the concentration gradient are varying constantly.
To actually solve this, engineers use Fick's second law, which, fair warning, leads to some pretty intense partial differential equations. To make it manageable in the real world, they rely on lookup tables for something called the Gaussian error function, or ERF. I know the math sounds a little intimidating, but this specific table is exactly what allows an engineer to precisely predict how deep the carbon has penetrated the steel at any given second.
All right, let's bring all this heavy math back to the macro world to solve our original problem. Section 6, Engineering the Real World.
So we are going to carburize a steel gear, exactly like the classic textbook problem. First, we identify our constants. Let's say our steel starts with a uniform 0.25% carbon. We pop it in an oven at 950 degrees Celsius and crank the surface carbon up to 1.20%. Our goal? To achieve exactly a 0.80% carbon target at a depth of 0.5 millimeter below the surface. Okay, step 2. We plug all these concentrations into the Fick's second law boundary condition equation. Step 3. This gives us an error function value, which we look up in our table to find a z-value of 0.392. And finally, step 4. With just a tiny bit of algebra, we solve for our one remaining variable, time.
And there's the answer, 7.1 hours. That is exactly how long that gear must bake in the high-temperature oven for those tiny carbon atoms to migrate via interstitial diffusion 0.5 millimeter deep into the solid steel lattice. If you pull it out too early, the case is way too thin. Too late, and it gets brittle. But if you hit 7.1 hours precisely, that gear will handle the raw, brutal torque of a highway sports car without shattering.
So the next time you look at a car, a tool, or even just a metal object sitting on your desk right now, ask yourself, what invisible atomic migrations are trapped inside the metal objects around you? Every hardened surface holds the quiet legacy of Fick's laws, extreme heat, and the relentless, microscopic dance of atoms. Thanks so much for joining me on this explainer. I really hope you found this as fascinating as I do, and I'll catch you next time.